Hi, in this video I will talk about self-supervised learning. Generally, a large labeled dataset is required to train a deep vision model with supervised learning. Obtaining labeled data has a cost. Amount of labeled data is small compared to unlabeled data. There is no labeling cost for unlabeled data. Amount of unlabeled data is very large compared to labeled data. In unsupervised learning, results are less accurate because there are no ground truth labels. In self-supervised learning, automatically generated labels are used as pseudo-labels. Hence the name self-supervised. Self-supervised learning uses only unlabeled data. Self-supervised learning uses large amount of unlabeled data without cost of manual labeling. So, self-supervision comes from automatically generated pseudo-labels. One example can be image reconstruction with convolutional autoencoder. Autoencoder has mainly three components. Encoder reduces the dimension, in other words, compresses input image. At bottleneck, image is represented as a low-dimensional vector called latent vector. And decoder reconstructs output image using low-dimensional representation in bottleneck. In this example configuration, label or target output image is same with input image. This autoencoder learns to reconstruct input image during training. Target output image is the input image itself. This means in this architecture, label is automatically generated just copying the input image. Input image is copied and used as pseudo-label. This autoencoder is trained on unlabeled data. During training, network learns discriminative visual features of images in the specific unlabeled dataset at hand. One thing to note is that this autoencoder is trained in supervised fashion, but it's not supervised learning. It is self-supervised learning because labels are generated automatically from unlabeled data. For a typical computer vision application, benefiting from self-supervised learning is a two-stage process. The first step, Pretext task, is performed with self-supervised learning. There is no human supervision, only pseudo-labels are used. This is feature learning stage. The second step, Downstream task, is performed with supervised learning. Human supervision is incorporated with labels. This is fine-tuning stage. In Pretext task, a convolutional neural network model is trained on pseudo-labeled data. Early layers of the model trained in Pretext task are used as the base for the model in Downstream task. In Downstream task, a new model is constructed using pre-trained base layers and is fine-tuned on labeled data for a specific computer vision application. For example, image classification or semantic segmentation. Knowledge gathered in Pretext task is transferred to Downstream task as starting point. If labeled data is limited for Downstream task, this is not a problem. Because heavy lifting is done in Pretext task using probably large amount of unlabeled data. Training this autoencoder on unlabeled dataset is an example of Pretext task. After Pretext task, early layers of encoder are used in Downstream task. Different Pretext tasks can be used to capture visual features in unlabeled dataset. In image generation with super resolution, label image is the original image. Input image is obtained decreasing the resolution of original image. In image colorization, label image is the original image. Input image is obtained converting original image to grayscale. In rotation prediction, input image is obtained rotating original image alpha degrees. Label is rotation angle alpha. And alpha is randomly chosen from this set. So rotation prediction is classification among 4 classes. In image inpainting, label image is the original image. Input image is obtained erasing some parts of the original image. For more details, take a look at these videos on my channel. And that's all for this video. See you next time.